Good morning, dear students. Today we're having the 13th practical lesson. So we started a new module, differential equations and series, and today's lesson will be about differential equations of the first order. Actually, what is a differential equation? Differential equation, so this is equation that contains derivatives or differentials, and the solution of the differential equation is a function that which with substituting which into the initial equation we will so it will be true. Let's start solving differential equations. The first type of differential equations of the first order are equations with separable variables. Let's start. So we have the following equation: y multiplied y e in power of 2x dx minus 1 plus e in power of 2x dy equals 0. This is an equation with separable variables because yeah, we can see that we can separate them. So dx, so x and y. So let's first of all separate them. So we have the following equality. So now what can we do? Let's divide the left part by this expression. So move x to the left. And it will be equal dy. Then let's divide by y. Yeah, let's move y to the right. We finished separating variables. And then we can integrate each of these expressions. We will integrate them. So first of all, calculating this integral. So it will be equal. Yeah, we will use differential entry technique. So differential of this expression. And we will receive logarithm of 1 plus e in power of 2x. So this expression is always positive. And what about y? And what about 1 over y? So let's write down the following. So logarithm of y plus, yeah, and we also need to write down the arbitrary constant, and in such cases it is convenient to write down it as a logarithm of constant. So we will receive the following equality. So what do we have now? Yeah, or actually, yeah, let's move better logarithms of c here. So we have the following equality. Yeah, it really doesn't matter where to move with constant because it can be any value without any initial conditions, without any boundary conditions. So Now let's uh, remove this logarithm, and what we will receive. So y equals c multiplied by this expression. So this is the solution of the differential equation. Actually, not always uh, solutions can be found in a explicit form, but in this case, it's possible. So, any questions about this exercise? I guess that no questions. Okay, so let's move to 1b. The following differential equation x, y prime equals 1 minus x square. Let's rewrite y prime as dy by dx, first of all. So to separate variables. What will we do now? Let's move x and dx into the right part. So y dy equals 1 minus x divided by x multiplied by dx. So now we will integrate both parts. So calculating this integral, so it will be equal 1 over 2 y square. And what about this integral? Yeah, let's rewrite it a little bit. So it is 1 over x minus x. And the answer will be a logarithm of modulo x minus 1 over 2 x square plus c. So the answer will be the following. So 1 over 2 y square equals logarithm of modulo x minus 1 over 2 x square plus c. So we cannot receive here the solution in the explicit form. Yeah, of course we can uh, uh, separate it by two, so into two branches. So minus square root of this expression plus square root of this expression, but actually it will be enough to leave it in such form. So any questions about this exercise? Okay, no questions. So now let's move to the next exercise. So task number 2. So we have the following differential equations. Y prime equals 4x plus y plus 1 in power of 2. How to solve it? We will use the following substitution. So this expression, 4x plus y plus 1, will be equal z. Then y prime equals 4. And let's first of all express y via z. So then y equals z minus 4x minus 1. So z is a function which depends on x. Then y prime equals z prime minus 4. So having the following equation, when substituting, so z prime minus 4 equals z square. So let's separate the variables now. So dz by dx equals z square plus 4. Yeah, and actually we will divide. So z square plus dz over z square plus 4 equals dx. Now let's integrate this expression. Both parts of it. So this integral, of course, will be equal to x. Okay, x plus c. And this integral will be equal arctangents of z. 1 over 2 arctangents z over 2 plus, okay, c is here. So now let's substitute also y. So y equals, yeah, z equals this expression. So 1 over 2 arctangents over 4x plus y plus 1 over 2 equals x. And what do we have here? Yeah, x plus c. Yeah, and by the way, we also can rewrite it into the explicit form. So why not? We can do it. So so let's do like this. So arctangents equals 2x plus c. Then this expression will be equal. Okay, let's even get rid of 2. So this expression equals 2 tangents over 2x plus c. Then y will be equal to tangents 2x plus c minus 4x minus 1. So this is the final solution in the explicit form. Any questions about this exercise?
Sorry, I have a question.
Yeah.
In the beginning, we had z square. Where did we get it from?
We
Little bit
substitute.
under, little
So
bit on.
we
Oh, yeah,
substituted this expression with the function z.
yeah. Ah, y prime is z square. Ah, okay, okay. I got it.
Yeah. Yeah. So
Okay. Oh,
uh,
that's why.
mm, okay. So this equation transformed to this equation.
Okay, I just didn't pay attention to this part. Yeah,
Uh,
thank you.
yeah. You are welcome. Any questions? More questions about this exercise? Okay, if no questions, we are moving to the next exercise. So task 3, yeah, 3a. So we need to solve given differential equations that are homogeneous with respect to variables. So let me first of all write down these equations, and then we will start solving them. So, x square, what's going on? X square plus 2xy dy. So this equation is a homogeneous equation, and how to solve it? Yeah, well, first of all, how to define that equation is a homogeneous. So it contains so variables x and y. They always are in power of 2. So so no, not power of 2. So they always have the same power. So in this case, power of 2, power of 2. So it's a polynomial of x and y. Power of 2, power of 2, and here power of 2 as well. How to solve it? We will divide both parts by x square. So, first of all, divided by x square. So 3 over... Yeah, we can also divide by y square, but let's divide by x. It is more convenient and more understandable. So we will receive the following expression. So 3y square over x square plus 3x over y plus 1 dx. Then it equals x, it equals 1 plus 2 x y over x dy. And here I made a mistake, y over x. Then we will do the following substitution. So y over x equals u. Then y equals, okay, let's do the full, let's write in one line. So y equals ux. Yeah, and u is a function that depends on x. So y prime equals u prime x plus u. So yeah, and yeah, let's first of all write down. So we will rewrite this expression. So this equation. So dy over dx. So the dy by dx equals uh, this fraction. And after the substitution, we will receive the following stuff. So 3u square plus 3u plus 1 divided by 1 plus 2u. And it equals x du by dx plus u. So now we will separate the variables and integrate this equation. So, first of all, let's subtract u from this expression, from both parts. So minus u minus u minus 2u square equals this expression. So now let's continue calculating. Yeah, let's continue first of all transforming the equation. So what do we have? U square plus 2u plus 1. Then yeah, let's move x into the left part. So dx over x multiplied by this expression and equals du. And now we will turn over everything. So dx over x equals 1 plus 2u divided by this expression du. Let me check if it, yeah, so if we have the same here, yeah, we have the same. So let's now let's integrate both expressions. So yeah, we'll write like this. So these expressions will be integrated. So it will be definitely equal logarithm of x plus c. I don't know if we really need to write here like logarithm of c. Not sure for now. So let remain like this, and after that, so if we need, we will change to logarithm. And what about this integral? Actually, what this integral will be equal? Yeah, let's substitute and subtract 1. Add and subtract 1. So what we will receive? So in this case, we have just a moment. So one minus 1 here. And here I will have the differential over this expression. Yeah, reminding you some rules of integration. And what do we have here? So a logarithm of this expression. And here actually what do we have? So minus it will be u plus 1 square. U plus 1 and all this expression in power of 2. And I also can write down like, so it will be in the numerator the differential of this expression, because 1 will be differentiated to 0. So actually it will be 2 logarithms of oh yeah, it is a perfect square, by the way. So 2 logarithms of u plus 1 and minus 1 over u plus 1. And now let's set both parts equal to each other. So received the general solution, but we need to return to the old variables. So u equals y over x, and we also need to substitute it. We need to substitute it everywhere. So this is the final solution. It is really hard to say if we can receive it in the explicit form or not, but such a form of the answer is acceptable. So, more questions? Or any questions about this exercise? Okay, I guess that no questions. And by the way, yeah, so we have the same answer here, and we really we don't need to waste time to check if we can express y explicitly. So now let's move to 3b. Let's have more practice with homogeneous equations. So we have the following equation: y prime equals y over x plus sine over y over x. So again, we do the following substitution: y over x equals u, then y equals xu, and y equals y prime equals u prime x plus u. So let's do the substitution into the initial equation. So we have u plus sine of u. Now let's separate the variables. So let's rewrite u prime as du by dx. And du by dx multiplied by x will be equal 1 plus 1 over u sine of u. Then okay, let's yeah, Bogdan, question?
Sorry, I think we could subtract u from both sides because you have plus u and on the left side
Yeah,
and
really.
plus u on right.
Yeah, we can do it. Thank you for your attention. Yeah, let we not uh, really make it difficult, but let's make it easy. So yeah, a nice catch, thanks. So we have the following equation. So du divided by sine of u equals dx by x. So now we can integrate both parts. I don't really remember the integral of coseconds. So let me look into the table of integrals. Yeah, because it is not such popular integral, but sometimes we need it. So it will be equal logarithm of module tangents of u over 2. And this here we will have logarithm of module x plus c. Okay, let's write down here as a logarithm of c. So received the following equality. And now let's remove a logarithm. So tangents of u over 2 equals cx. And now let's write down the following. So tangents of u over 2 equals okay, u equals arc tangents of 2cx. No. U equals to arctangents of cx. Yeah. So now correct. And now let's return to old variables. So y over x. And here we can express, so we can receive explicit form of the solution. So 2x multiplied by arctangents of cx. Any questions about this exercise? Okay,
I
no
guess no
questions.
questions.
So, yeah.
I guess no questions.
Okay, if no questions, let's move to task number 4. And let's solve the following equation. So we need to uh, reduce, so we will solve the equation with reducing it to homogeneous. Uh, First of all, how can we reduce it? We need to verify that, so we need to check that we can reduce it, first of all, to homogeneous. We need to calculate the following determinant. So with the coefficients near these variables. So here will be 1, here -1, 1, and 1. So let's calculate. So actually 1 plus 1, so it equals 2, and this determinant is not equal to 0. So as it is not equal to 0, we can reduce it to the homogeneous. Yeah, and by the way, we can, so how can we reduce it to the homogeneous? We will do the following substitution. So x equals x1 plus h, and y equals y1 plus k. Now let's substitute everything into this equation. So dy 1 by dy by dx1. So here we have x1 plus h minus y1 minus k plus 1. And here x plus h plus x1 plus h and plus y1 plus k. So we received the following uh, expression. Then how we actually can find these coefficients? Yeah, so we will solve the system which these coefficients, so h and k form. But yeah, first of all, let's rewrite it. So x minus y, yeah, moving it here and here. And let's check if, yeah, everything is correct here. So, yeah, now we will receive we have to solve the following system of equations. Where it is, so this equation equals 0, and this equals 0 as well. So let's solve it. Equals 3. So we have, so if we add both parts, we will receive 2h equals 2. So h equals 1. And what about k? K equals 2. So found. So now let's substitute everything into this equation, and what we will receive. Yeah, so actually we will just, so if we substitute h and k into this equation, we will, these constants will be eliminated. So we received the following equation. So what are we doing now? Mhm. Yeah, now we can we can make a substitution like we did before. So y 1 equals ux1 uh, and uh, dy by dx1 equals uh, du by dx1 multiplied by x1 plus u. Okay, and then let's also divide both, so numerator and denominator by x. Okay, let's divide them here. So if I divide by x, I will receive, so 1 minus y1 over x1, and here 1 plus y1 over x1. So here what we received, so the following expression. So we will have u here and here. So now let's solve this equation with respect to u, first of all. So will be equal, so 1 plus u here, and 1 minus u minus uh, minus u minus u square. Yeah, it seems that it's correct. So now let's separate variables. So what we will receive? So du. Okay. So first of all, let's write down like this and multiplied by. Hmm. So let's turn over the fraction. Yeah, and by the way, it will be minus 2u equals 1. So then du equals dx 1 over x1. And of course, yeah, we will integrate them. So let's calculate this integral and this integral. So this integral, of course, will be equal logarithm of module x1 plus c. And if we need, we will turn it to the logarithm. And what about this expression? So okay, here not such convenient, not really convenient integral, but it is absolutely manageable to calculate it. So let we remember how to. Oh yeah, we really. Oh yeah, we can uh, use differential entry technique here. So what we will receive? So 1. Oh yeah, here 2. Sorry. 2 minus 1 minus 2u minus u squared. So what will we have? 1 plus u and 2 minus 1 plus u squared. And actually, yeah, du equals in this case, so it will be the same as d or 1 plus u. Okay, so we have the following integral. So it is a high, not a high logarithm, but so 1 over 2. Stop. I even yeah, so I can even simplify it. So really, if we differentiate so this expression, so I will receive uh, minus minus 2 1 plus u du. So really uh, we can even write in a more simple way. So minus 1 over 2 and differential of this expression. Yeah, so I always don't so I don't always see as you that we can simplify something. So we have the following logarithm. So this the following expression, and now we write down that logarithm of x. Oh yeah. So here it will be logarithm of c. Why not? So this expression equals, yeah, Bogdan, you have a question?
Uh, yeah, why is it minus 1 over 2 if it was just minus 2?
Uh, because we have 1 here, so coefficient
Ah,
here is 1, yeah, so not to
yeah.
break the equality.
Hmm. Okay.
So the following stuff received, so cx1 equals 1 over square root of this expression. Uh, and then, yeah, let's also uh, return to old variables. So first of all, to variable, so to variable y. So we have y over y1 over x1. And also remember that we did some substitution. So returning to old variables, so cx, okay, a x plus 1 equals y plus 2 over x plus 1. So this is the final answer. We can maybe even extract y here from the square root, but it's not really so convenient. So let we leave it like this. Yeah, here it is even uh, more simple, in a more simple way written as the answer. So any questions about this exercise? Okay. If no questions, we will have a break and then we will solve more exercises. So we will solve linear differential equations and Bernoulli equations, total differential equations, and Cauchy problem. And now have a break for 5 minutes. Okay, let's continue. So now moving to different to linear differential equations. So we have so the first equation, y prime equal y prime plus 2y over x equals x cubed. Why it is a linear equation? Because y prime has power of 2 and power of 1, and y also has power of 1. So how to solve such equations? It is a non-homogeneous equation, a linear non-homogeneous equation, because we have not zero in the right part. So we have a free member. So how to solve such equations? There are two methods: Bernoulli's method and the method of variation of arbitrary constant. Let we use now a method of variation of arbitrary constant, and Bernoulli method we will use for Bernoulli's equation. So how to use arbitrary constant variation method? We need to solve the correspondent homogeneous equation first of all, and a linear homogeneous equation. It is always equation with separable variables. So dy by dx equals minus 2y over x. Then so dy over y equals minus 2 dx over x. So after that we will integrate both parts. And what we actually will receive, so logarithm of y equals c equals minus 2 logarithm of module x plus logarithm of module c. And then we will simplify it. So y equals c over x square. Now, what are we doing? So we set c as a function that depends on x. So then y equals c from x divided by x square. We need so how to find the function c from x? We will substitute it into the initial non-homogeneous equation. So what do we have? So we need, so y prime, we will differentiate this function. So x in power of 4 in the denominator, and so c prime x plus c plus 2 plus 2c over x over x cubed and equals x cubed. Then, okay, let me check if everything here is correct. So yeah, 2cx cube here. Yes, so c prime x plus c. Plus plus 2cx. Yeah, forgot about it. And here cx square, by the way. Yeah, just lost this square. So c prime x square plus, and minus, by the way, minus 2 cx over x in power 4. Then let's expand this expression. So what do we have? Cx c prime over x square minus 2 cx cube plus, and plus this part. And always when you use method of arbitrary constant, c always must be eliminated. If after this substitution into the initial equation c is not eliminated, so look for the mistake. It means that you have a mistake. But here it is eliminated, and it means that we substituted correctly. So this is correct solution. Then continue finding c prime. So c prime equals x in power of 5. So then c equals 1 over 6 x in power of 6 plus c. Let's use such a wave, for example, just to set so to show that it is arbitrary constant, not a function. So after we found c, we will write down the solution. So we will substitute it into this equation. So y equals such expression. So 1 over 6 x in power of 6 plus c, and this expression divided by x square. Let me check here. Yeah, correct. Any questions about this exercise? Okay, I guess that no questions. So task B will be your home task. So now we will skip it. And here you will have to, first of all, to express y prime, so derivative as y prime, so to transform it a little bit, but I guess it will not be so hard for you. Then let's move to Bernoulli's differential equation, and we will use Bernoulli's method. So, by the way, do you have any questions about this exercise, about linear equations? Or no questions?
No questions.
Okay, no questions. So let's continue. Yeah, so here we have Bernoulli's differential equation. So how it usually looks. Y prime. Yeah, let's first of all write it down. So plus 2x y and equals 2x cube y cube. So it is a little bit similar to the linear equation. So we have uh, power of 1 for prime and power of 1 for y, and we also have the member for which y can be any power. So different powers. How to use the Bernoulli method? we write y as a product of functions u and v. Functions u and v, they are functions that depend on x. So let's differentiate this product. So y prime equals u prime v plus u v prime. And let's substitute it into the equation. So u prime v plus uv prime plus 2x uv equals 2x cube u cube and v cube. Then we need to regroup them a little bit. So how to regroup? We need, okay, let's, for example, move here, let's move u out of brackets. So u prime v plus u v plus u, and here v prime plus 2x plus 2xv, and the right part without changes. Yeah, let's check. Yeah, this it is correct. So we need to solve the system of the following system of equations. Now, so this equation, so we need to find, so this expression will be equal to 0, and then this expression so will be equal to this. Yeah, because yeah, so actually this is how Bernoulli the method works. So we set this expression equal to 0, so it means that this expression equals this expression. So let's find v from the first equation. So v equals, so v prime plus 2xv equals 0. So then now let's let's separate the variables. Dv by dx equals minus 2xv. So dv over v equals minus 2x dx. So now let's integrate both parts. So logarithm of v equals minus 2x. Then v equals e in power of minus 2x. Let me check it here. Yeah, v equals minus yeah, v equals minus 2 e in power of minus x square, by the way. Yeah, because integral of this expression will be yeah, so minus x square. My bad. Then what about u? So now substituting v into this expression, so what we will receive? U prime e in power of minus x square equals 2x cube multiplied by u cube and multiplied by e in power of minus 3x squared. Then yeah, let's start separating variables. So du by dx equals by exponent equals yeah, and we also divide by u cube. So equals 2x. Okay, let me write down like this and just erase u in power of 3. Then so du. Okay, let me do like this. So what remains in the left part and what in the right part. So I divide by this expression, so I multiply by e in power of x squared. So here will be minus 2 and dx. So found. Then we will integrate this expression. So this integral is quite simple. So it will be equal to minus 2 minus 1 over 2 u square. So found this integral, and what about this integral? So let me check if I go, oh yeah, I'm going correctly. So this integral not such easy, so it doesn't look so convenient. So we will do the following stuff. So we have 2x multiplied by x squared. And what do we actually see? That we have here differential of x squared. So 2x dx equals dx squared. And now let's also substitute that x squared equals t, just for our convenience. So t e in power of 2t dt, e in power of minus 2t dt. So now we can integrate by parts. So okay, let's write to like this. U1 equals t du1 equals dt. Yeah, it really so we don't always have enough of letters to mark something. So v1 equals e in power over minus 2t dt, and then v1 equals minus 1 over 2 e in power over minus 2t. So integrating by parts. So, and we have the following integral: 1 over 2 integral, so e in power of minus 2t dt. and minus 1/4 e in power over minus 2t. And then, yeah, let's also move exponent out of brackets and 1/4, so minus 1/4 e in power of minus 2t t plus 2t plus 1, and return into old variables. So x square here and 2 and x square here. So calculated this integral. Let me check if what do we have here. Yeah, actually the same stuff. Yeah, and let's also write down the constant here. So yeah, u will be equal. Okay, now let's yeah. So let's first of all write down these expressions. So we actually can move. So remove minuses. And what about c? Actually, we don't care about the sign now because c is any real number, so it doesn't matter. What next? Let's also multiply by 2. Yeah, and multiplication by 2. No. So minus, yeah, it is important not to use minus here. So now multiplying by 2. And then we will find u from this expression. So u will be equal plus minus 2 square roots of 1 over this expression. Yeah, let me check. Yeah, and yeah, 2 here, by the way. So now we will write down the answer, the final answer, the solution. So as we remember that y equals uv, so v equals e in power of minus x square. Yeah, so plus minus this exponent multiplied by this square root. So this is the final answer. Any questions about this exercise? Okay, as I see, no questions. So now we are moving to the next exercise. So equation in total differentials. So total differential equation. And yeah, first of all, we need to check if it is the equation of total differential. So we have let's write it down first of all. So x minus y square plus 3 dy. So equals 0. So actually, we need to differentiate. Yeah, to check that we have total differential of the function. So p equals this expression, and q equals this expression. Let's differentiate them. So dp by dy equals 1. And what about dq by d1 by dx? It will be equal 1 as well. So these derivatives are equal. So it means that we have total differential. So total differential equation. And how really to solve a total differential equation? We will just find the so how it will be found. How it will be found. So we will restore this function by its total differential. So with using the following formula. So what about, yeah, let me remind you the formula. So uxy equals, so from 0 to x, p from x, y with index 0. Yeah, x from x0. So this expression plus what about q? So from y0 to y, q from xy dy plus c. So we will restore the function by its total differential. And what about x, y, x0, y0? We can we can choose the point 0, 0. Because the domain contains it, so let's do it. So now let's restore it by total differential. So 0 here, 0 here. So p from x and y0. So x plus 1. And here, this expression. And now let's differentiate. Oh, not differentiate, but integrate. Sorry. So we have 1 over 2x square plus x for first integral, and for the second integral, xy minus 1 over 3y cube plus 3y plus c. So if I substitute 0 here and 0 here, I will receive 0. So let's consider that we substituted it. And actually, it will the final solution will be the following. So the generic solution looks like this. So this we set this expression equal to 0. Or we can we can drop c here and write just so this expression equals to c. So it will be the generic solution of the equation of the total differential equation. As we see, total differential equations are easy to solve. So it is really good when we have the total differential equation. We cannot find it explicitly because we have different powers of y, so we will leave it like this. Any questions about this exercise? Okay, I guess that no questions. So now let's look through the exercise B. So we have the following equation. So x square, so we will not solve it now, but just look through. So x square y square minus 1 dx plus 2x cube y dy equals 0. So if we differentiate p and q, we will see that they are not equal. So the initial equation is not a total differential equation. But uh, we can see that, so we can find the integrating factor. It is the function that can the function that depends on x and can uh, uh, and it can transform the initial equation into the total differential equation. So it is usually, yeah, so it can be found, it is found by the following equation. Yeah, so how to find the right part, we find it from this expression, so from this equation. So we can find mu integrating factor from this expression. And when we found it, we multiply all the whole equation by the integrating factor. And after that, we receive total differential equation. After we integrate, yeah, here is a mistake. Actually, it must be dq1 by dx. So equals. Yeah, by the way, I can even yeah, let me write like this. After that, we'll fix it. Then, then after that, we just we can find it by the following formula. We cannot set here x0 as 0 because we divide by x. So we set 1 as x0 point because it is included into the domain. And this is the final, so the generic solution. Any questions about this exercise? Okay, no questions. So now let's move to the next exercise. Um, we will find the partial solution of a differential equation that satisfy the given initial conditions. So we will solve Cauchy problem. Well, actually, what does it mean? We will find the generic solution, and after that we will find a constant c. So let's write down the first equation. So the Cauchy problem, actually Cauchy problem, it is the equation with the given initial condition. So, and it is the initial condition or Cauchy condition. So just reminding it. So 1 plus x square and y from 0 equals 1. It is usually set 0, but uh, so because usually we solve differential equations, so we find function which usually depends on time, so on the initial moment of the time. So what do we have? We have an equation with the separable variables. So first of all, we are finding the general solution. We separate the variables and integrate. So dy by this expression equals dx by this expression. So let's integrate. So arctangents of y equals arctangents of x plus c. So what do we have to do now? We need, so let we extract, so what we solve explicitly. Let's express y. So y will be equal tangents over of this expression, arctangents x plus c. So this is the generic solution, general solution. And now what about c? How to find c? We just substitute, so instead of y, we substitute 1 from the initial condition. And for x, I substitute 0, so this point. And I receive actually tangents c. So then, so tangent c equals 1, it means that c equals p over 4. So the final solution, so partial solution is the following. Y equals arctangents of x plus p over 4. And that's it. So we found the generic solution, or the partial solution, solved the Cauchy problem. Any questions about this exercise? Okay, if we have no question, if you have no questions, let's see if we can, if we have enough time to solve some more equations. Yeah, here y from 1 equals 0. Let's just look through it. So we have the homogeneous equation because functions of one dimension. So we do the following substitution: y equals ux and u equals y over x. So received the following equation, found u. So it looks like this, and we actually cannot find the solution in the explicit form. Yeah, maybe we can, but it's not really so easy to do. But we have everything for finding so for finding constant c. So we substitute 0 by 1. So we substitute 0 instead of y, 1 instead of x, and we receive that c equals 1. And we just write down the partial solution, but y is not in the explicit form. Oh, by the way, yeah, well, I actually not really sure how can we express in the, oh, maybe like inverse hyperbolic function can be received, but it's not really so easy. Any questions about this exercise, about the whole lesson, about previous lessons? Okay, if you have no questions, let we finish for today. Have a nice day, stay safe, and thank you for your attention.
Thank
Goodbye.
you.
Thank you.
Goodbye.
Thank you for this lesson.
Thank you for
Take
us.
care.
Have a nice day.
Bye, and you too.